Hello everyone, my name is Jason Gregerson, and this video is going to be a video key for the practice exam for exam 2. So here's the exam, and we'll just start by going through the true and false. So number 1, part A says a set of two vectors could be a basis for R3. So to investigate this, we might grab two vectors in R3. So I'm just going to make up two vectors from R3. And for me to determine whether these vectors are a basis, I would have to show that they are linearly independent and that they also span all of R3. To answer both of those questions, I can actually just create the matrix whose columns are these vectors, and I could row reduce. And to determine whether these things are linearly independent, I'd be looking for if there was a pivot position in each column. And that's certainly possible in this case, but the other thing to consider is that for them to span R3, I would have to have a pivot position every row. And since I only have two columns, I can only have at most two pivot positions. There's no possible way I could have a pivot position in each row. So these two vectors could not possibly span all of R3. So in this case, the answer is false, because these two vectors could not possibly be a basis for R3. Similarly, four vectors could not possibly be a basis for R3, because if I added two more vectors, no matter what they were, if I row reduced, the most pivot position I could get would be 3, and so there's no way I could have a pivot position for each column. So in this case, if I had four vectors in R3, they could not possibly be linearly independent. All right, B says if H is a subspace and U and V are in H, then U plus V must also be in H. And so really this is one of the definitions of our vector space, that it must be closed under vector addition. So for H to be a subspace, it has to be a vector space in itself, and then it must be closed under addition, which says that the sum of any two vectors in H must also be in H. So this is true by the definition. C says if A is an m by n matrix, then the null space of A is a subset of Rm. And the next question says if A is a m by n matrix, then the column space is a subspace of Rm. So we can really answer both of these questions using the same analysis. So I'm going to look at the equation Ax equals 0. Ax equals, actually we'll start by looking at Ax equals some vector b. If A is an m by n, then dimensions of my vector x must be n by 1. And then the product, A times x, must have dimensions m by 1. And now if we think, what is the null space of A? The null space is a set of all x's such that Ax equals 0. So it's really sum of the possible inputs out of all of the possible inputs. It's just the ones that map to 0. But just to be able to input it into this equation, it has to be an n by 1 vector. Therefore, the null space is a subset of Rn. So this first one would be false. Now the second question is about the column space. Well, the column space is all of the linear combinations of the columns of A. But this matrix equation is the same thing as a vector equation, which is really representing all of the linear combinations of the columns of A. So the column space is essentially all of the outputs, all of the possible B's. But we can see that just to satisfy the dimensions of this equation, that B would have to be an m by 1 vector. Therefore, it would have to be a subset of Rm. So the second one is true. All right, E. E says if A is a n by n, and the determinant of A is equal to 0, then the matrix is invertible. So let's start with kind of a simpler case. Let's look at a 2 by 2. So we're talking about square matrices here. If I look at a 2 by 2, A, B, C, D, we have a formula for the inverse. It should be 1 over the determinant of A times, and then we switch the values on the strong diagonal and change the signs of the value on the weak diagonal. But the important piece for this true and false questions is that coefficient in front is 1 over the determinant of A. So if the determinant of A is equal to 0, this value is undefined. Therefore, we don't have an inverse. So actually, if the determinant of A is equal to 0, then the matrix is not invertible. So this one would be false. The next one says if A is an n by n matrix, a square matrix, and 0 is an eigenvalue of A, then the matrix is invertible. So let's write out that eigenvalue equation. Ax equals lambda times x. So if this equation is true, then lambda is an eigenvalue of A and x is the associated eigenvector. But if we're looking at 0 as an eigenvalue, that would simplify to this equation. But then if A was also invertible, we would be left with just this. That would be the only possible solution. But we're looking for non-zero vectors as eigenvectors. And so this would say that there does not exist any non-zero x's, which means there couldn't be any eigenvectors, which means this couldn't possibly be an eigenvalue. So this one must be false. Part G says every subspace must contain the zero vector. So this one is true based on the criteria needed to show that a subset is a subspace. We said that to show that a subset is a subspace, we don't have to check all 10 properties of being a vector space, because many of them just come from the fact that we're dealing with a subset of a vector space. But rather we have to check 3 main properties. We have to see if it's closed under addition, closed under scalar multiplication, and we have to show that the zero vector is in the subset. So this one is true. H says if the matrices A and B are both square, then the determinant of A times the determinant of B is equal to the determinant of the product. This one is true. Part I says a n by n matrix A is diagonalizable if and only if A has n distinct eigenvalues. And this one is going to be false, because it is only true in one direction, where if and only if implies it's true in both directions. We could say that if A has n distinct eigenvalues, this piece, then yes, it is true that A is diagonalizable. But if we go the other direction, if A is diagonalizable, this would say that then A has n distinct eigenvalues. And it turns out we can actually have diagonalizable matrices that don't have n distinct eigenvalues. There are some cases where we have repeated eigenvalues, where the matrix is still invertible. J says if the null space of A is equal to the zero vector, then A is invertible. So what is this one saying? Well, the null space is the set of all x's such that ax equals 0. So all the x's that map to the zero vector. So they're saying if the null space is only the zero vector, that's another way of saying that the homogeneous equation has only the trivial solution, and that is one of the properties stated in the invertible matrix theorem. So this would be true. If A is similar to B, then AX equals B has the same solution as BX equals B. And this one is false. Two matrices that are similar have the same eigenvalues, but it certainly doesn't mean that they have the same solutions. If A is similar to B, then A has the same eigenvalues. And this one is true. Our definition of similarity is that A must equal P times B times P inverse for some matrix P. And one of the key properties of similar matrices is that they do have the same eigenvalues. All right, so question number 2. Let the following set of vectors be a basis for a vector space. Then answer the following questions. Part A says, what is the dimension of V? Well, the dimension of a vector space is the number of vectors in its basis. So here I have a basis of 2 vectors. The dimension of V should be 2. The next question says, is this specific vector in V? Well, if this vector is in V, I should be able to represent it as a linear combination of the basis vectors. In other words, there should be some constant times the first basis vector plus some constant times the second basis vector that bring me to my vector 2, 0, 3. So to find out if there are these constants, I would just solve this vector equation. But solving this vector equation is the same thing as solving the matrix equation. And to do that, I would just form the augmented matrix. In this case, I only need one row operation to bring it to RREF, and that would be to take R1 minus R3, in which case I'll get 1, 0, negative 1. Actually, there is one more operation. To be in RREF, I should actually switch to R2 and R3. So I will write this row here and leave my row of zeros at the bottom. And so from here, I can see my solutions would be C1 is equal to negative 1, and C2 is equal to 3. So I would say that yes, this vector is in V because there is a linear combination that would bring me, of the basis vectors, that would bring me to 2, 0, 3. Part C says what are the b coordinates of x, i.e., and here's the notation for the b coordinates. Well, the b coordinates are just the weightings of each basis vector that bring me to x. So in this case, the b coordinates are just -1 and 3. All right, question number 3 says, given the set of vectors, answer the following questions. First question, is the set of vectors a basis for R3? To be a basis for a space, I have to show that these vectors, the set of vectors, are linearly independent, and also that they span all of R3. To answer both of these questions, I can simply form a matrix whose columns are these vectors. And then I would row reduce to REF. In this case, to get to REF, I would just switch row 3 with row 2. Now I'm in REF. I see that I have 3 pivot positions. And more importantly, I see that I have a pivot position for every column. That tells me these 3 vectors are linearly independent. But I also have a pivot position for every row. That tells me that these set of vectors span all of R3. So I would say that yes, they do form a basis for R3. Part B says let S be the standard basis. So the standard basis looks like these 3 vectors. And it says if the coordinates of x and the standard basis are 1, 0, 2, find the coordinates of x with respect to our new basis. So the coordinates of this vector with respect to the new basis are really just the weightings of each basis vector that give us the coordinates in the standard basis, which is 1, 0, 2. And so all we're really doing here is finding these right constants that map to 1, 0, 2. But this vector equation is the same thing as a matrix equation, which we solve using an augmented matrix and row reduction. So I will simply form my augmented matrix and do the row reduction. In this case, I will once again just switch row 2 and row 3. And then I will take row 2 minus row 3 to get 0, 1, 0, 2. And then my last step will be to take row 1 minus row 2. I'll get 0 here, and I'll get 1 minus 2 is a -1 here. So here my solutions would be C1 equals -1, C2 equals 2, and C3 equals 0. And these are the weightings of the basis vectors that should bring me to 1, 0, 2. So this tells us that the coordinates of x with respect to this basis are -1, 2, and 0. Now part C. Part C is if I know the coordinates in the b basis, how do I find the coordinates in the standard basis? Well, once again, these coordinates are just the weightings of each of these basis vectors. So this is telling me that 2 times the first vector plus 1 times the second vector plus 0 times the third vector, what is the output of that? In this case, if I just add these values up, I would get 2, 0, 0 plus 1, 0, 1 plus 0, which is equal to 3, 0, 1. And so these would be the coordinates in the standard basis. Number 4. We're given a matrix A and we need to answer the following questions. The first one says, is this vector in the null space of A? Well, the null space of A is a set of all vectors that map to 0, all the solutions to the homogeneous equation. So to see if this is a solution, I could just take A and times it by x to see if I get 0, 0. So I could just take 1, 2, 1, 0, 1, 1, and multiply it by my vector. The result would be, well, if I take it and multiply by the first row, I get 1, -2, 1. And then times the second row, I would get 0, -1, +1. As I simplify, it looks like I get 0 and 0. So I would say yes, x is in the null space of A. Part B says find a basis for the null space of A. In other words, find all of the vectors that are in the null space, or at least a representation for that space. So to find all the solutions to the homogeneous equation, I'm just going to solve that equation. So I'm going to write my matrix, and I'm going to have it augmented with the zeros. I'm going to do my row reduction. In this case, it's already in REF, so I have to do the back substitution to put it in our REF. So I will take row 1 minus 2 times R2. I will get 1, 0, -1, and 0. So my equations look like x1 minus x3 equals 0, and x2 plus x3 equals 0. And it looks like x3 in this case is a free variable. So now when I form my solutions, x1 is equal to x3, x2 is equal to negative x3, and x3 is just free. So this looks like the solutions are any multiple, any value of x3, times 1, -1, 1. So the solution space, the set of all solutions, is really just any multiple of this vector. So this vector is a basis for that solution space. It is a basis for the null space. Part C says find a basis for the column space. Well, the column space is a set of all linear combinations of the columns. So it might be natural to think that the set of those three columns would be a basis. Those three columns certainly span the column space of A, but the question is, are they linearly independent? So to determine that, I would simply look at that matrix and find the linearly independent columns of A, and they would actually form a basis for the column space. Now, because this matrix is already an REF, I can see the pivot positions, which mark the linearly independent columns. Thus, 1, 0 and 2, 1 would be a basis for the column space. And then D says, what is the dimension of the column space of A? Well, once again, the dimension is just the number of vectors in the basis, so in this case, the dimension would be 2. And then just as a quick check of our answer, we see the dimension of the column space is 2, but we have one vector in the basis for the null space, so the dimensions of the null space is 1, and the sum of those two dimensions should equal n, where we have A is an m by n matrix. It's the number of columns. Question number 5. Given this matrix, which row reduces to this matrix, answer the following questions. So in this problem, we're going to do the same kind of analysis that we did in the previous problem, except now the work of row reduction has already been completed for us. So the null space of A is a subspace of R what? Well, once again, the null space is a set of all vectors that map to 0. So if this is A, I take it and multiply some vector x, how big would x have to be just to do the multiplication? Well, here it has to match the number of columns. So this would be x1, x2, and x3. So that means all the x's that we input, they all live in R3. And so it's some subset of that R3 space that actually map to 0. Now we want to find a basis for the null space of A. To find a basis, we would find all the solutions. But to solve the equation AX equals 0, we would simply look at our matrix A and row reduce it. But we already have the row reduced version here. So we are just going to generate our equations from this row reduced version to look at x1 minus x3 equals 0, x2 plus x3 equals 0, and x3 is a free variable. Now note here there is no x4. There are 4 rows, but there are only 3 columns. And it's those columns that identify our variables. So our solution in this case looks like x3, negative x3, and x3, or any multiple of the vector 1, -1, 1. Therefore, this vector is a basis for our null space. Part C says, what is the dimension of the null space? Well, since our basis has only one vector, our dimension is 1. Now we continue on. It says the column space is a subspace of R what? Well, the column space is a set of a linear combination of the columns of A. It's all of the b's in the equation AX equals B. It's all the possible outputs. But if each of the columns in A have 4 components, so each one of these columns is an element of R4, and we take a linear combination of them, we'll still get vectors that are in R4. So the column space is a subspace of R4. Part E says find a basis for the column space of A. Well, the basis of the column space should be the linearly independent columns of A. To find out which columns are linearly independent, we would go through that row reduction process and see which columns had pivot positions. We've already done that here though. So here's a pivot position and here's a pivot position. It turns out the first 2 columns are pivot columns. That tells me the first 2 columns of my matrix, so this column and this column, that those 2 vectors are linearly independent, and therefore those 2 would form a basis. So the basis for the column space are these two vectors. And the last question is, what is the dimension of the column space of A? Well, if we have two vectors in the basis, the dimension of the column space must be 2. And so once again, we see that the dimension of the column space is 2, the dimension of the null space is 1, and the number of columns in our matrix A is 3. And those values should add up like that. Question number 6 says, if this is our matrix A, find the determinant of A. Show all work. So we are going to do a row expansion to find this determinant. And so the most important thing is to expand down a good column or row. In this case, I'm going to expand down the first column. So first I'm going to establish my signs for my coefficients. This is the 1, 1 position, so it'll be positive, then negative, then positive as they alternate throughout my matrix. So my expansion looks like taking this value, 1, times the determinant I get when I eliminate that first row and first column. So I'm left with this little block of values. So I need the determinant of that mini matrix. Then I get minus 0 times the determinant I'm left with when I eliminate that row and column. So this would be 2, 3, 0, and 4. Although in this case I really don't care because the 0 will eliminate that term anyway. And then lastly, I have plus 1 times the determinant I'm left with when I eliminate that row and columns. And there I'm left with 2, 3, 1, 1. So then I continue to evaluate. I get 1 times this determinant. Well, this determinant is just this product minus this product. So that's 4 minus 0, which would be 4. Then I have minus 0 plus 1 times 2 minus 3. So it looks like I have 4 minus 1, which is 3. Number 7 says if A and B are both n by n matrices, and the determinant of A is 3, and the determinant of B is 2, what is the determinant of the product of AB? In this case, the determinant of the product of AB is equal to the product of the individual determinants. So it looks like this one would be equal to 6. Number 8 says find the determinant of the following matrices. The first one is the 2 by 2, so it should just be this product, 4 times 1, minus this product, 2 times negative 1 is negative 2. So it looks like the determinant is 6. And what about the determinant of this matrix? Well, in this case, I'm going to expand down the third column. And so once again, I'll adjust my signs here. I have positive, negative, positive. So the determinant should look like negative 1 times the subdeterminant, 2, 1, 0, 1. And then it should go minus 0 times something and plus 0 times something. So those just disappear. I'm left with negative times 2 minus 0, or negative 2. And for this last one, once again, it is a 2 by 2 matrix, so it should just be 4 minus a negative 2. In this case, 6. Number 9 says find the eigenvalues and eigenvectors for the following matrices. So here's my matrix A. And to find the eigenvalues, I look at the determinant of A minus lambda I, which is equal to the determinant of 4 minus lambda minus 1, 2, 1 minus lambda. Remember, that's because identity is just a matrix with 1 on the diagonals, and if I multiply that by lambda, I'm just going to get lambdas on the diagonals. When I take a matrix and subtract it, I'm just subtracting the lambdas on the diagonals. So now I do this determinant. I take the product 4 minus lambda times 1 minus lambda minus this other product, so minus a negative 2. And then I expand everything to get 4 minus lambda minus 4 lambda plus lambda squared plus 2. This should be equal to lambda squared minus 5 lambda plus 6. And this actually factors into lambda minus 3 and lambda minus 2. And our question here is, when is this determinant value actually equal to 0? And it turns out in this case it's equal to 0 when lambda equals 2 and lambda equals 3. Now that I have the eigenvalues, I have to go back and find the eigenvectors. So I start with one of my eigenvalues. I'm going to say when lambda equals 2, I need to solve A minus my lambda value times I times x equals 0. I need to solve that homogeneous equation. So to solve that, I first calculate this matrix. It's just A with 2 subtracted on the diagonals. So that's 2, negative 1, 2, negative 1. And I'm going to solve this homogeneous system. In this case, if I take row 2 minus row 1, I would get a row of all zeros, which I expect because I expect there to be non-trivial solutions to this homogeneous equation. And those equations look like 2 times x1 minus x2 equals 0. And it looks like x2 is my free variable. And so my solutions look like x2. And x1 looks like it should be equal to, if I add x2 to the other side and divide it by 2, I get 1/2 x2. So this should be my eigenvector for any choice of x2. Now, of course, to make a nice clean eigenvector, I would like to choose a good value of x2 to clear my fractions. If I let x2 equals 2, then my eigenvector looks like 1 and 2. But once again, an eigenvector could be any multiple of this, any choice of x2. So when lambda equals 2, my eigenvector is 1, 2. Now I go back to when lambda equals 3. I do the same thing. I look at a minus 3i times x equals 0. So now I'm subtracting 3 on the diagonals. I will get 1, negative 1, 2, and negative 2, augmented again with 0. Once again, I know these rows must be multiples of each other for there to be non-trivial solutions. And I can see if I take row 2 minus 2 times row 1, I really will get a second row of zeros. So the equations here are x1 minus x2 equals 0, and once again x2 is free. So my eigenvector in this case looks like x1 should be equal to x2, and x2 is free. So it looks like any, and this is the eigenvector for any choice of x2. So this eigenvector could be 1, 1 if I choose x2 to be 1. So when lambda equals 3, this is my associated eigenvector. Now let's look at number 10. Part A says an n by n matrix is diagonalizable if the matrix has n linearly independent, and the answer here is eigenvectors. If we have linearly independent eigenvectors, then we can diagonalize our matrix. Now we can certainly get that if we have n distinct eigenvalues, but we can get that in other cases as well. So the criteria here is we need to have enough linearly independent eigenvectors. B says a linearly independent set that spans a space is called a blank for the space. And this is really the definition of a basis. A basis is a set of vectors that are linearly independent and that span a space. C, a set of all solutions of the homogeneous equation, ax equals 0, and this should be the 0 vector, is called the null space. The null space of the matrix A. Part D says the set of all linear combinations of the columns of the matrix A is called the column space of A. So these are just some general definitions. 11 says let A be this matrix with eigenvalues given to us and the corresponding eigenvectors also provided. And this is answer the following questions. We should diagonalize A, in other words, express it into this form. Well, to do this, we just need to find P and D and P inverse. But P should be the matrix that's formed whose columns are the eigenvectors, in this case 1, 0 and 3, 1. The matrix D should be the matrix that is diagonal and has the eigenvalues as the diagonal entries. Now notice an alternative here would be to use 3, 1 and 1, 0, but then to create the associated D with the eigenvalues also interchanged. That would also be acceptable. Now if I choose this P and this D, the only other step would be to calculate P inverse, which should be 1 over the determinant. In this case, my determinant would be 1. It'd be 1 over 1 minus 0, times the matrix, where I change the values on the strong diagonal, so I swap these two 1s. I change the signs in the off diagonal. So that would look like 1, negative 3, and 0 and 1. So, now that I've calculated this, the diagonalization would look like A is equal to P times D and P inverse, which is like 1, negative 3, 0, 1. And of course, on the exam, I should take these three values and multiply them out to see if I really do get to A, to see if I've done it correctly. Part B says use the information from the previous part to write an expression for A to the fourth. And it says I just have to write out the expression. I do not have to multiply out the matrices. So the idea here is that if A equals P times D times P inverse, then A to the fourth would equal P times D to the fourth times P inverse. But better than that, I actually know a good way to calculate D raised to the fourth power. Because it's diagonal, I can actually take those components and raise them to that power. That's not true in general, that's true for a diagonal matrix. Thus, A to the fourth would be 1, 3, 0, 1 times 3 to the fourth, 0, 0, 1 to the fourth, which is just 1, times 1, negative 3, 0, 1. Question 12 says, here's our matrix A, and it's equal to this product. And this is what are the eigenvalues and the respective eigenvectors for our matrix A. What we see here is this product is really in the form P times D times P inverse. And if that is the diagonalization of A, then we can see the eigenvalues should just be the diagonal entries of our matrix D. So our eigenvalues are lambda equals 4, 2, and 1. And then the associated eigenvectors would just be the columns of our matrix P. So our first eigenvector would be equal to 1, 0, 1. Our second eigenvector would be equal to 1, 0, 0. And our third eigenvector would be equal to that last column, 0, 1, 1. So we can really just pull these values after we see that diagonal representation. And now part B here says use the information from the previous part to write an expression for A to the fourth. So once again, we're just realizing that A to the fourth should just be our matrix P times D to the fourth times P inverse. And once again, the value is seeing that I have my matrix P, but because D is diagonal, D to the fourth is really just those diagonal elements raised to the fourth power. Once again, that's not true in general, but that is true for a diagonal matrix. So this would really just be the representation for A to the fourth. All right, that's the last question for this practice exam. So this concludes this video. Thank you.